Hello, I'm Dr. Devendra Kumar. Welcome back to this lecture series on electrochemistry. So this is our second lecture. In the last lecture, we discussed about like how the ions move in the solution with the different speeds. Their ionic mobilities are different, and I'm just showing you that slide just to review it in very quickly in a couple of seconds. That how H ions, cupric ions, copper 2 plus and hydroxide ion move with a different speed in the solution, and that can be visualized with the help of this noise experiment, right? So, and this experiment helps us to demonstrate that different ions move with the different speeds or ionic mobilities in the solution, right? So since their speeds are different, and if we pass the electricity through the solution, the number of ions discharged going to different electrodes should be different, and we should get different number of moles of cations and anions at different electrodes, cathode and as well as at the anode. But intuitively, number of ions discharged at the electrode are different, same, right? So since they have different speeds, so different number of ions should be going to the cathode and anode respectively, right? So towards the cathode it will be the cations, and towards the anode it will be the anions going. But in total, the number of ions discharged at the cathode, which will be cations, and number of ions discharged at the anode, which will be the anions, are equal. So how is that possible? So to demonstrate that, so there is this Hittorf's theoretical device, this method, which helps us to understand how these two ions are equal in magnitude. So basically in this theoretical device, it's just a theoretical concept only, right? So in this theoretical device, Hittorf's theoretical device, or also known as Hittorf's method, we consider the solution in three different compartments. One adjacent to cathode, near the cathode electrode, which is bound to the negative side of the external battery, is the cathodic compartment, and another one is central one, and one near to the anodic electrode will be the anodic compartment. All right, so the whole solution is divided into three different parts: anodic, central, as well as the third one is cathodic, right? So now here ions will move from the cathodic compartment once we apply electricity. So once we connect to the circuit, this cell, from the cathode, negative ions will move, which is the anions, and they will move towards the anode, towards the positive side. Similarly, from the anode, it will be the cations that will move through the central compartment ultimately to cathode, because cathode bears the negative charge. Right. So this is how it will move. The cations will move from the anodic compartment, right, from here. Anions will move from here, and central compartment just provides a method, a medium to transfer of these ions. All right, so this is how we divide this solution, and as long as this uh, electrolyte, the cation and the anionic part, are paired, they will not be discharged. Only the bare part, once they are present individually, they will be discharged at the electrode. They will undergo electro oxidation or reduction at the corresponding electrode. As long as they are as the in the form of pairs, as shown in this slide, over here and over here, they will be sorry they will be, they will stay as such, right? So let's move to the next slide. Now let's consider a case, once on applying the electricity, neither of the cation nor the anion move, right? So they stay as such. So this is the situation before, the applying the electrolysis. This is cathodic compartment. You can see 8 pairs of the electrolyte in the cathodic compartment, 8 pairs in the central, 8 pairs in the anodic. You can assume any number you want, but I have considered here 8 pairs each in each compartment. Now, once we apply electricity, we are going to consider a case where neither the cation moves nor the anion moves. All right. So now, what will be the, how many ions will move from cathode? Anions? No, none, because it is the case where neither of them moves. So this will be the ultimate situation in end, which is same as the previous one, right? So hence number of ions discharged at each electrode will be, do you see any bare cation or anion in anodic or cathodic compartment? No, hence they will be zero. They are all paired, so they will not be discharged. They will stay as such in the solution, and hence number of cations discharged at the cathode are zero. Number of anions discharged at the anode are 0. Right. So now let's consider the second case where two cations move and two anions move. This means this is the case in which both the ions have equal mobility. Their mobility, ionic mobility is same. All right. So this is the situation: 8 pairs in the cathodic compartment, 8 in the central, 8 in the anodic. Right. And now we apply electricity. So how many cations will move from the anode? 2. So these two cations will move from through the central compartment ultimately here. So now we will have two cations extra here in this compartment, and similarly two anions move, and anions will move from here, right? So therefore we will get two cations bare because of the movement of two anions from here, and two extra cations from the anodic compartment, right? So we got four uh, bare cations here in the cathodic compartment. Central compartment will stay as such because it is just providing a simple medium to the transfer of these ions. And in the anodic compartment, we will have four bare anions, similar to the cathodic compartment, right? So how many cations will be discharged at the cathode? We count the bare number of ions only: 1, 2, 3, 4. So it will be 4. So 4 cations will be discharged at the cathode, and at the anode again we count only the bare, the individual anions without the pair. So these anions are 1, 2, 3, 4. So 4 anions are discharged at the anode, right? Similarly, we can work upon the uh, another case where the ions have unequal mobility, ionic mobility, and in this case I have considered that the anions moves faster in the given time. So this means in that given time more number of anions will go move. So I have considered two cations and three anions, which simply says ionic mobility of anions is more. And if you count that, so in the cathodic compartment, what will we have? We have movement of three anions from here, right? So three cation will be left behind, and also two cations will move from here. So ultimately we will get five different bare cations in the cathodic compartment, and those will be discharged. Central will remain as such, right? And similarly in the anodic compartment it will be five anions left behind, and those will be discharged at the anode. So in total, how many cations are discharged at the cathode? 5. And how many anions are discharged at the electrode anode? 5. All right. So we can also add this up from here. If you see, total number of cations and anions discharged at the different electrodes are same, even though different number of cations and anions are moving. But the cations and anions being discharged at the individual electrode are same, right? And which is the sum of the, this 5 comes from 2 plus 3 in both cases. So you can simply add up. So let's do this little bit quickly, where the cation has more ionic mobility. So again, it will be how many cation, 3 cations moves and 2 anions move. So how many ions will be discharged? It will be 5 in each case, 3 plus 2. So you can simply add those up, and find out how many cations and anions are discharged at cathode and anode respectively. All right. So this method helps us to demonstrate that how, even if the mobilities are different, how the same number of cations and anions are discharged at the individual respective electrode, that is cathode and the anode. All right. So this is Hittrof's theoretical device. Now we look at this transport number, a new definition from here, a new parameter to define the speed of the cations and anions in the solution. So from the Hitto's theoretical device, we know that even if their mobilities are different, the number of ions discharged at each electrode are same, right? And these are simply can be find out by addition of the how many cations and anions move. Those will be the number of the ions discharged at that electrode. So that's the outcome of these. For example, if 2 cations and 3 anions move in a given case, it will be total number of 5 cations and 5 anions will be discharged at the respective cathode and anode. All right. So, and now, according to Faraday's law of electrolysis, number of ions discharged at the electrode is proportional to total quantity of electricity passed through the solution, and hence total quantity of electricity will be the number of ions discharged. And how many ions are discharged? Let's consider the last case, 5 at the cathode, 5 at the anode. So which is the result of both cation and anion? So it will be sum of the mobilities of the both the ions, cations and the anions. Also, quantity of electricity carried by the particular ion is proportional to mobility of the particular ion. So combining these two, we get this definition of the transport number. It is the total current, fraction of the total current carried by the each ion is called the, in the solution, is called the transport number. If U plus is the mobility of cation and U minus is the mobility of anion, transport number for the cation is current, fraction of current carried by the cation divided by total current. So fraction of current by cation is proportional to U plus, and total current is ionic mobility of cation and ionic mobility of anion. Similarly, you can get T minus as the U minus divided by U plus and plus U minus. And if you add those up, you get transport number of both of them give you a unity, and hence these transport numbers are fractional numbers. Also, this mobility of the ratio of this mobility of cation to mobility of anions are proportional to the fall in concentration at the around those electrodes, whether it is cation or anion. All right. So for example, when 2 cations moved and 3 anions move in the same time, mobility of cations to anions is 2 by 3. Of course, if you simply divide those up, how many cations move? 2. How many anions move? So U plus by U minus is 2 by 3. And in the given time, the concentration falls by 2, right, around the anode, and for around the cathode it has fallen by 3 ions, and hence the same concentration, fall of concentration is around the anode to the around of fall of concentration around cathode is also 2 by 3. All right. And so transport number can also be defined as fall of concentration around anode divided by total fall in concentration around cathode plus anode, right? Or the total number of ions discharged at the electrode. Also, in terms of gram equivalents, it will be fall of concentration in gram equivalent around anode divided by gram equivalent of the uh, that stuff deposited or discharged at the electrode. Okay, so let's consider a solution of lithium chloride, sodium chloride, and potassium chloride, right? And transport number for these follows the same order. Potassium has the highest one, sodium has the medium, and falls in the middle. Lithium is the lowest. Why is it so? So chloride is common here. So ultimately, the conductance comes from these ions, and they follow this order. Why would that be? K plus is the largest ion, right? So it should move slowly, but it has the largest conductance. So it is counterintuitive. It comes down to the again the same factor. It is the charge by size to charge to size by ratio, that is charge density. And since K plus has bigger size, it is charge density is smaller, and hence it is hydrated to a lower extent, and therefore it can move a little bit more quickly in the solution as compared to lithium ion, which is heavily hydrated. And that is why speed of the potassium ion, ionic mobility of potassium ion is highest, lithium ion is lowest, sodium falls in the middle. Okay, so now our next topic is conductometric titrations. So what are these titrations? So basically in this titration we try to find out the concentration of analyte usually, uh, or we try to find out what is the pH, pKa of the solutions through this conductometric titrations. So usually what we do is we try to follow this reaction as the uh, reaction happens. We try to follow the conductance of the solution as a function of time, right? And of course conductance depends upon size, all right, as well as how many, it is the nature of ion. Basically size is the nature, let's say lithium plus and sodium plus. So size or the nature of the ion, and also how many number of those ions are there in the solution, right? So over here we what we plot is we plot conductance on the y-axis, and on the x-axis we plot the volume of the titrant that is being added, and we plot their changes, whatever the change we record, and from there we find out equivalence point, and hence we determine the required parameter. All right. So during this titration, what happens is one of the ions either precipitates or one of the ions is totally replaced by the another ion, basically, right? So that's what happens here. So let's consider strong acid versus strong base conductometric titration. So HCl versus NOH. So in this SL2 solution of HCl, we add slowly uh, sodium hydroxide solution from the burette with the help of the burette, right? And the ionic equation will be HCl totally ionized in the solution because of it is a stronger electrolyte. Sodium hydroxide is added from the burette, 1 ml, half ml at a time. So ultimately, HN and OHN combined give you unionized water, and then sodium chloride is formed, which being the stronger electrolyte totally dissociates in the solution. So in the nutshell, what is happening, Cl ion, chloride ion is spectator here, so you can basically kind of cancel it out, right? So basically what is happening here is H plus is being replaced by sodium plus. Now if you remember, which one of these has the higher conductance or ionic mobility? H plus, because it moves with a different spatial mechanism, growth type mechanism in the solution by hydrogen bonding. So initially H plus is replaced by sodium plus, which has a lower conductance. So that's why we see a sharp fall in conductance with time. All right. And slowly, once all of this acid is neutralized, then sodium hydroxide that is being added leads to an increase in the conductance further, and intersection of these two profile gives you the equivalence point. So this cross should be here, right at here. So this X determines the equivalence point. From there we can find out the strength of the NOH and other parameters in other reactions. All right. So what happens? Conductance first decreases due to consumption of H ions, and after neutralization, after this equivalence point, it increases due to the addition of sodium hydroxide, which is both sodium and hydroxide contributes here to the conductance. All right. So now consider the second case where a weak acid is taken. The profile is shown here. So first the conductance increases little bit more slowly, and then after the equivalence point rapidly. So let's try to understand how this profile is being generated here. Once a weak acid is titrated like acetic acid with the against the strong alkali such as sodium hydroxide. So to a solution of acetic acid which is poorly uh, unionized in the solution, so I will just write as such, and sodium hydroxide is added, you get sodium acetate, which is completely being a strong electrolyte, which is completely ionized, and H2O is formed, right? So basically what you are getting is from an unionized solution, you are getting more ions. So that's why there is an increase in the conductance. And then after the equivalence point, end up adding load of sodium hydroxide, and that is why this sharp increase in conductance is there, and intersection of both of these gives you what basically the amount of acetic acid by applying N1V1 and N2V2. All right. So once the acid is completely neutralized at this intersection point, introduction of this sodium and hydroxide ions gives you steep, sharp increase in the conductance. Okay, so that is why increase in conductance is more here. Okay, so that is weak acid versus strong acid. Now let's consider once we have mixture of a strong acid and a weak acid. Now we know which one will be totally dissociated. Strong acid, HCl. So profile will be like that of HCl, which is like this sharp decrease. And once all of this is gone, acetic acid will be H from the acetic acid will be neutralized, right? And then once all of the acetic acid is gone, intersection of that with the N further, there will be increase in the conductance due to addition of NaOH only. So it is just the combination of those two different profiles which we have discussed. So if you combine those both two, you get this, right? So that is why, and intersection B refers to how much HCl is there, and from B to C, it is not initial to the C, it is from B to C. It refers to how much acetic acid is there in the solution, right? Okay, now let's consider another case. If you have strong acid like HCl and that is titrated against a weak base, all right, so profile is such that first it decreases, then becomes constant. Let's try to understand why this happens. So HCl is totally being a strong electrolyte is 100% dissociated. So HCl is there. You add ammonium hydroxide, which being a weak electrolyte is very feebly dissociated. So now OH ion combined with H ion to give you unionized water, right? And then ammonium chloride is formed, which is being a strong electrolyte. So you get more number of ions in this solution, right? And H ion is effectively being replaced by the NH4 plus and Cl is spectator, right? So Cl minus is spectator. So basically that conductance is common, and effectively H plus is being replaced by NH4 plus, and conductance of NH4 plus is lower. You just remember that H plus is the ion with a has a highest ionic mobility. All right, so that's why there is a decrease till all of that NH4 HCl is titrated, and thereafter once all of this HCl is gone, if you add further NH4OH, which is a weak electrolyte, the increase in conductance will be less. It will almost stay constant. And intersection of both of these two lines will give you the equivalence point, which will be a measure of how much HCl is there in the solution. Right. So this is how we can explain this graph. Now precipitation. If the precipitation is happening, for example, a reaction of silver nitrate against potassium chloride. So silver nitrate is a strong electrolyte. So silver nitrate we will write in the ionized form. KCl is also a strong electrolyte. We are adding KCl from the burette. And now if both of these combine, silver chloride is formed, which is sparingly soluble in water. So it forms these precipitates. And potassium nitrate is formed, which also is a strong electrolyte. Now effectively what is happening is nitrate is common, so silver plus is being replaced by potassium plus ultimately. So now conductance will depend the relative ionic mobility of silver plus and as well as potassium plus, and it happens that potassium plus has a higher ionic mobility. So since silver plus ion is replaced by potassium plus, there will be a slight increase in the conductance first till all of that silver nitrate is titrated, and thereafter a steep rise because you are adding a lot of KCl, which is a stronger electrolyte. So lot number of ions you are adding. So that is why it will give rise to a large increase in the conductance, and intersection of these two profiles will give you the equivalence point. All right, so this is it is. And usually in the conductometric titration, what we do is we take more stronger solution in the burette, right? And or basically if those two, if two solutions are being titrated, one is 0.01 molar and another one is 0.1, the stronger solution, which is 0.1 molar here, should be taken in burette. All right. This is to avoid the dilution effect, because with dilution, as we recall, the conductance increases just because of the dilution. So to avoid this dilution effect, change in conductance due to a dilution only, the solution in the burette should be such that it should have a higher concentration as compared to solution in the conical flask. So what are different advantages of conductometric titration? One, you do not really need to add an indicator here. You must be recalling your experiments from the laboratory, where you will add phenolphthalein, methyl orange indicators. You will look for a color change. So we don't really look for color change. All we look for is conductance, which we get from the instrument, record those readings and plot the graph, right? So even colored solution can be titrated, because now you don't look for any color change, which will may or may not be obvious to your eyes. So colored solution can be titrated. And also very dilute solution and weak acids and weak bases can also be titrated, because their conductance profiles can easily be monitored. Thirdly, no special care is needed for the endpoint, whether you add 1 ml extra, 2 ml extra, because in the end, you are obtaining your equivalence point just by intersection of those 2 points using the graph, right? So it doesn't really matter how much you add, even though you may not want to add like 50 ml at a time, you will do 1 or 2 ml at a time, but still no special care is taken near the endpoint. So these are the couple of advantages of the conductometric titrations. So we will end up this lecture here, and in the next lecture we will cover about different kind of electrodes, concentration cells, galvanic cells, and the electrolytic cells. So thank you so much for your attention, and hope you enjoyed the lecture. Thank you.